Welcome back to the Deep Dive. This is the place where we give you a shortcut to, well, to really getting your head around some complex ideas. And today, we are leaving the clean theoretical world behind. We're done with dry water, and we're diving straight into the real, messy, chaotic world of what the sources call the flow of wet water.
That's a great way to put it. I mean, so much of early physics education is about these ideal systems,
Yeah.
fluids with no friction. But in the real world, it's that friction viscosity that just dominates everything. So our mission today is to see what happens when you add that one thing back in. How does it turn simple flow into turbulence and chaos?
I love that. Moving from the elegant theory to the uh, beautiful mess of reality. So, okay, if we're building this world of wet water, where do we start? What's the one foundational idea we just have to accept first?
It all starts right at the boundary. At the surface of any solid object, it's an experimental fact called the no-slip condition.
No slip condition.
Oh,
Okay.
It just means that any real fluid, whether it's water or air, has zero velocity right at the surface it's flowing over. The very first layer of molecules is stuck.
Wait, hold on. So if I'm driving down the highway, the air hitting my windshield is moving, 70 miles an hour. But you're saying the very thin layer of air actually touching the glass is perfectly still.
Perfectly still relative to the glass. Yeah, it seems completely wrong, I know. But it's all about the attractive forces between the fluid's molecules and the solid's molecules. They basically they stick together.
Okay, my mind's a little blown. So if the layer at the surface is at zero and the fluid a tiny bit away from it is moving fast, get this incredibly steep change in speed.
A massive velocity gradient, exactly. And that is what the fluid is fighting against, that internal shearing, that difference in speed between adjacent layers of fluid. That's where viscosity comes from. It's the resistance to that shear.
It's the stickiness.
It's the stickiness, and to measure it, we imagine the simplest possible case, the classic two parallel plates experiment.
Right. So you've got a puddle of fluid between two plates.
Yep. One is fixed, it's not moving. The other, the top one, you pull at a constant velocity, let's call it V0. To keep it moving, you have to apply a force. You have to overcome that internal friction.
And that force must have something to do with how fast you're pulling and how thick the fluid is.
Precisely. The force per unit area, what we call the shear stress, is directly proportional to the velocity gradient. So how quickly the speed changes across that gap.
Okay, so the faster you pull or the smaller the gap, the more force you need.
Exactly. And the constant that connects them, the proportionality constant, that's it. That's the coefficient of viscosity. We call it eta. High eta, you've got molasses. Low eta, something like gasoline.
And you mentioned something that I think people miss. It's not a fixed number for a given fluid, right?
Not at all. It's hugely dependent on temperature. I mean, for water, just going from room temperature down to near freezing, the viscosity almost doubles. It gets twice as sticky.
Wow. Okay, so that's viscosity in a simple one-direction flow. Now we have to do the hard part. We have to bake this idea of friction into the full three-dimensional equations of motion for a fluid. And this, I hear, is where things get complicated.
Complicated is an understatement. This is where you get into the famous Navier-Stokes equations, conceptually at least.
Yeah.
The problem is that the viscous force, it ends up depending on the second derivatives of the velocity.
Okay, stop right there. Second derivatives. For those of us who aren't, living and breathing calculus, what does that mean physically? Why is that such a big deal?
It's a huge deal because second derivatives are the mathematical language of diffusion, of spreading out. Think about heat. The equation for heat flow has second derivatives, and what does heat do? It diffuses. It spreads from hot to cold.
Wow.
The math is telling us that something in the fluid is also diffusing.
And that something is what we call vorticity.
That something is vorticity, which is, just a measure of the local spinning motion of the fluid. And here's the beautiful part. When you rewrite the full, messy equations in terms of vorticity, you get something that looks exactly like the equation for heat diffusion.
Which brings us to Feynman's brilliant smoke ring example. A smoke ring is a perfect, clean little vortex. Why doesn't it just spin forever in a perfect fluid?
In a perfect non-viscous fluid, it would. But in our wet water, that vorticity, that concentrated spin, is like a drop of hot dye in a cold tank. Viscosity makes it leak out. It diffuses into the still air around it, spreading the rotation out, making the vortex bigger, slower, and weaker until it just vanishes.
So viscosity is why nothing in the real world spins forever. It's a diffusion of rotation.
That's a perfect way to put it.
Okay, this is amazing.
Yeah.
But now we have these incredibly complex equations with all these variables: density, velocity, viscosity, the size of the object. How on earth do scientists predict what's going to happen? It seems impossible. We need some kind of a
Real-
cheat code.
And we have one. It is without a doubt the master key to all of fluid dynamics. It's the Reynolds number. We just call it R.
The Reynolds number.
It's a stroke of genius. Someone realized that if you scale all the variables in the equations in just the right way, by a characteristic size and a characteristic speed, the whole chaotic system boils down to depending on just one single dimensionless number.
And what is that number actually measuring? What's the physical meaning?
It's the ratio of two forces. It's inertia versus viscous forces. Are the go forces the momentum of the fluid winning? Or are the stop forces the internal stickiness winning? That's what R tells you.
So a high Reynolds number means inertia is dominant, the flow is just plowing ahead.
Hmm.
And a low Reynolds number means viscosity is in charge and everything is slow and sticky.
You've got it. And the most powerful idea here is the principle of similarity. If two different flows, I don't care if it's air over a wing or water around a submarine, if they have the same Reynolds number, the flow patterns will look exactly the same. They will be geometrically similar.
That's incredible. So that's how you can test a tiny model in a wind tunnel and know exactly how the full-size version will behave.
As long as you match the Reynolds number, it's the key.
All right, let's see it in action. The classic example is flow past a cylinder, like a pole in a river. Tell me what happens as we slowly crank up R as we increase the speed.
Okay, so at a really, really low R, like close to zero, viscosity is king. The flow is beautiful, it's smooth, it's symmetric, it just oozes around the cylinder and joins back together perfectly on the other side.
Very calm, very orderly.
Very orderly. Now, speed it up a bit. Let's say R gets to around 20. Now inertia starts to matter. The flow can't quite make that sharp turn around the back, so it separates. And right behind the cylinder, you get two little vortices that are just stuck there. They're stable. They just sit there and spin.
Okay, so we've got a little wake now.
Yeah.
What happens if we keep pushing the speed?
This is where it gets fun. Around R of, say, 100, those two little vortices become unstable. They can't stay put. One breaks off the top, then one breaks off the bottom, and they start shedding alternately, creating this beautiful staggered pattern of vortices flowing downstream.
The Kármán vortex street.
That's the one. And it's not just pretty. Each one of those shedding vortices gives a little kick, a little sideways force to the cylinder.
Which is the source of that dangerous vibration that can bring down bridges or smokestacks if the frequency is wrong.
Exactly. It's the flow itself, creating a rhythm, creating a force. Now, keep cranking up R into the thousands, and that orderly street breaks down into a completely chaotic, turbulent wake.
And you'd think the drag, the force on the cylinder, would just keep going up and up and up.
You would think so, but then something truly bizarre happens. At a Reynolds number of around 1,000,000, the drag force suddenly abruptly drops.
Wait, what? You make it go faster and the drag goes down? That makes no sense.
It's one of the most counterintuitive things in all of physics. What happens is the flow becomes so energetic that the boundary layer itself, that tiny layer of fluid right on the cylinder's surface, becomes turbulent.
So you have chaos right on the surface.
Yes, and that chaotic, turbulent boundary layer has more energy. It can fight against the pressure changes, and it manages to cling to the surface of the cylinder for longer before it separates.
Ah, so the wake behind the cylinder gets smaller.
Much narrower. And since most of the drag at high speeds is pressure drag from that big, low-pressure wake, a smaller wake means dramatically less drag. It's amazing. Local chaos makes the global flow more efficient.
There's a perfect lesson in how wet water just refuses to follow our simple intuitions. Okay, let's wrap up with one final, very clean example of this progression to chaos. Couette flow.
Right, the fluid between two rotating cylinders. This is like the perfect laboratory for studying instability because it's so contained and controlled.
So you have an inner cylinder that starts to skin. What do we see?
Well, at first, at low speeds, the flow is completely smooth, laminar. The fluid just shears perfectly. But then you hit a critical speed and bam! The flow spontaneously breaks up into these perfectly stacked, horizontal, donut-shaped vortices. We call them Taylor vortices.
So it goes from smooth to this incredibly structured wavy pattern.
A beautiful, stable pattern, but you keep increasing the speed, and those perfect donuts start to get wavy themselves. They start to twist and oscillate. It's not quite turbulent, but it's this incredibly complex, sort of quasi-periodic state.
And
finally, you push it far enough, and all that structure dissolves into complete, irregular, chaotic turbulence.
that whole progression, from simple to structured to wavy to chaos, all in one simple setup. It really is the entire story of this deep dive in a nutshell.
It is. It shows that the incredible complexity we see in nature, in weather and galaxies, it's all hidden inside these relatively simple-looking fundamental equations.
The equations themselves aren't the problem. The difficulty is solving them and finding all of this unbelievable richness that's buried inside.
We have the laws that govern the flow of water, but we still to this day cannot predict the detailed structure of turbulence from first principles.
So wrapping this all up, what's the big takeaway for you listening at home? We've gone from dry water to wet water. We saw how viscosity and the no-slip condition create the whole game. We learned about the Reynolds number, the master key that lets us compare flows at different
And
scales.
we saw how even the simplest setups can produce this staggering journey from order to chaos, from the Kármán vortex street to Couette flow.
I think the most profound lesson here is qualitative.
Hmm.
It's the idea that even when you know the fundamental laws of physics, the systems they describe can have features, like the structure of turbulence, that are so complex they remain, for all practical purposes, unpredictable.
It means there's always more to discover, even when you think you have the rules figured out.
A pretty deep thought to chew on. Thank you so much for joining us for this dive into the sticky, swirling, and absolutely fascinating flow of wet water.